Hassan's Maths channel. I'm now answering question number 8 from the October-November 2022 Pure Mathematics P3 paper. This is paper 3, variant 3, from the Cambridge 9709 specification. And this question here is initially about differentiation, and then it goes on to numerical methods and iteration. So first of all, it says the curve with the equation y equals x cubed over e to the power of x minus 1 has a stationary point at x equals p, where p is greater than 0. So it says show that p is equal to 3 times, and you got 1 minus e to the power of negative p. So basically, we have to focus on this word, stationary point. Okay, we have a stationary point at x equals p. Now, the stationary point is a point where the gradient of the curve becomes 0. Okay, at the stationary point, we know dy dx is equal to 0. The gradient of the curve is equal to 0. So we have to differentiate this expression, and we have to equate it to 0. Okay, and when it's equated to 0, x is equal to p, and we can find the value of p then. So now, we have an expression y equals x cubed over e to the power of x minus 1. Now, what you should not or cannot do in a situation like this is you cannot just differentiate the numerator and differentiate the denominator separately. I can't just say 3x squared over e to the power of x and done. No, you can't do that. Right? That's what some students actually try to do. Okay? It's something which is quite a common mistake for those who haven't really studied properly the P3 material. But no, we cannot do that. We have to use what's called the quotient rule, right? If it's a product of two separate, functions like x cubed times e to the power of x, if it's a product, we have to use the product rule, okay? Here we're going to use what's called the quotient rule, okay? Now, the quotient rule is given in the formula sheet. The quotient rule is given in the formula sheet, and it's something which I'm just going to bring up now. I just copied it from there. All right, so here we've got both the product and the quotient rule as given in the formula sheet. On the top it says, f of x here is f dash of x. So this is the original function, and this is the differentiation of that. Okay, so you have a quotient of two separate functions, then, this is how it, what you have to do. Basically, you have to take the denominator multiplied by the differential of the numerator minus the numerator times the differentiation of the denominator, okay, divided by the denominator squared. So in this case, we have to call u x cubed, and we have to call v e to the power of x minus 1, okay? And we have to find du dx, which is 3x squared, and we have to find dv dx, which is e to the power of x. When you differentiate e to the power of x, it stays the same. If there's a number multiplying the x, or there's some other function in there, you have to also multiply by the differential what's inside the function. In this case, it's just e to the power of x. And if you differentiate x, you get 1, so you have to multiply by 1. And the minus 1, when you differentiate it, becomes 0. So we end up with this. Now we got to follow this pattern for differentiation. So dy dx is equal to, so you're going to multiply v times du dx. So these two multiplied, which is 3x squared times e to the power of x minus 1. And then you're going to have minus u times e to the power of x. So it's going to be x cubed times e to the power of x all over. And you're going to have v squared, which is e to the power of x minus 1 all squared. Okay, so what we know is that when x equals p, then at that point dy dx is equal to 0, because that's where we have the stationary point, right? So what I'm going to do is I'm going to replace the x with p and the dy dx with 0. So I have 3p squared times e to the power of p minus 1, okay, minus p cubed times e to the power of p all over e to the power of p minus 1 squared equals 0. So this has to now become the same as this expression here, right? It must look the same as this. Okay, so when I have this over here, just to keep it in mind, we have to make sure that this ends up being like this. So the first thing we can do is we can multiply both sides by e to the power of p minus 1 squared, in which case we got 3p squared times e to the power of p minus 1 minus p cubed times e to the power of p equals 0. And what I'm going to do now is I'm going to just expand the whole thing. So 3p squared times, in fact, I'm not going to do that because I see I have something that I need here. So what I'll do is I'll actually do something a bit more, make life easier. I'll see that p squared is common in both of these main terms. So I'll take out the p squared as common. Then I'll have 3 times e to the power of p minus, the minus is down there, sorry. E to the power of p minus 1. Okay, and minus, so let me just make that bracket the same as that one. Minus, I've taken out p squared, so I've got p times e to the power of p. Close that bracket. Okay, so that's the main bracket there that I've made, equals 0. So I've taken p squared out of these two main terms. All right, so now we have, I've taken p squared out. So either p squared equals 0, and we know they've told us that p is greater than 0. Okay, and we know that as p is greater than 0, therefore p squared can't be 0, therefore p can't be 0. So that's not, we can't write p equals 0. The other solution is where this product is equal to 0. So we have 3 times e to the power of p minus 1 minus p times e to the power of p is equal to 0. Right, so I can say 3 times p minus 1 equals p times e to the power of p, and we have to in the end make it look like this. Okay, as we can see, it has to look something like this. So what we can do next is I can divide both sides by e to the power of negative p. Sorry, there's something missing here. What did I write here? Sorry. Wrote that all down wrong for some reason. 3 times e to the power of p minus 1. So you shouldn't be in a rush. So divide both sides by e to the power of p. Now, if I divide this side by e to the power of p, I'm left with p, which is what I want on one side. If I divide this side by e to the power of p, I have 3 over e to the power of p times e to the power of p minus 1. Now, if I multiply through by this, 3 over e to the power of p times e to the power of p is going to give me just 3. So let me just, because I want to have it like this, I'll leave the 3 on the outside, and I'm going to multiply by e to the power of p. So e to the power of p, or you can say 1 over e to the power of p times e to the power of p is 1. And you're going to have minus 1 over e to the power of p. This is like 1 over e to the power of p times minus 1 over 1. We're left with this is equal to p. So now I can say that finally that p is equal to 3 times 1 minus, and you can write this on top with a negative power, e to the power of negative p. And that's exactly what we had to show. Right? So there's the answer to part A. So part A is all about basically differentiation and what's called the product rule. Now part B is related to what's called numerical methods and iteration. So I'm going to go through that now. So it says verify by calculation that P lies between 2.5 and 3. Okay, so what I'm going to do is I'm going to name this, give this function a name. I'm going to call it f of p. So first of all, what is f of p? I have to rearrange this to make it say equals 0. So I have p minus 3 times 1 minus e to the power of negative p is equal to 0. Once I've done that, once I've made it say equal 0, I'm going to name it fp. fp is equal to p minus 3 times 1 minus e to the power of negative p. All right, and that is the function now. So we got to show that p, the root, lies somewhere between 2.5 and 3. All right, so what we have to do is you have to find out what f2.5 is, and we have to find what f3 is. Now, if the root lies somewhere between them, there will be a change in sign between them, which I'll explain in a couple of minutes once I've just done the calculation. So here we don't have any trig involved with this, so I don't have to worry about radian mode or anything. Okay, I just have to put these numbers in. So I'm going to put 2.5 into this expression here and see what it becomes. So I have 2.5 minus 3 times 1 minus, I'm going to have e to the power of minus 2.5. Minus 2.5. Okay, so that gives us one answer, which is negative 0.2537. Negative 0.2537. Negative 0.2537. Continue on. And now we're going to do the same, but with putting 3 inside this function. So I'm going to go back to where I wrote 2.5 and just change that to 3. Sorry, 2.5. Okay, so that's right. That's 3 minus 3 times 1 minus e to the power of minus 3. Okay, good. That will give us 0.1493. Okay, 0.14. What was it? Sorry, forgot there. 14939. And continue. There's a 936. Well, let me just say we'll finish there. So here we can see very clearly that between these two there is a change in sign. So basically, what we can understand from this is, supposing we have a sketch of the graph between 2.5 and 3. Right? Now we can see that at 2.5 it had a negative value, and 3 it has a positive value. So somewhere between 2.5 and 3, it must have crossed through the x-axis, right? So as we can say, okay, it is a continuous function. Continuous function. It's not like an asymptote or something in between. And there is a change of sign. A change of sign. Okay, that means there must be a root. There must be a root in this interval. Okay, so that's how we answer part B. You have to show that there's a change in sign between these two calculations. That means the graph must have crossed the x-axis somewhere between these 2 points. All right, and that's how we prove that there is the value p, the root of this lies somewhere between those two. Right, now for part C, it says use an iterative formula based on the equation in part A to determine p correct to 2 decimal places. Give the result of each iteration to 4 decimal places. So we need to use the same equation here. This is called the iterative formula. Now for the final part of this question, we have to use the iterative formula, or use an iterative formula based on the equation in part A to determine p correct to 2 decimal places. So this is basically the iterative formula. We form an iterative formula to solve an equation that can't be solved by normal means by making one of the variables in the formula the subject. Right, so we're making x the subject of the formula, and in such a way that there's also x's inside the formula. So it's not really making it a subject of the formula properly, but it's like, this is how iterative formula is formed. So we're gonna basically, this will mean that p time, or pn, not p times, pn plus 1, the next value of p that we have to find, is going to be equal to 3 times 1 minus e to the power of pn. So basically, you put the first value of p you choose in your iterative formula in this place here, and then that takes out another value of p. And that will lead you to another value of p. When you calculate that, that'll give you the next value of p that you got to use and put it in the same place. So you put, for example, here we'll probably start with 2.5 because p lies somewhere between 2.5 and 3. So if we start with p1 being 2.5, then P2 is going to be found by taking P1 and replacing the P in it by its value, which is 2.5. Okay, and then that will give us P2. So we've got to write this down to 4 decimal places, right? And then P3 will be found by taking this value and putting it back into the same place. And P4 will be, so you keep going until your expression starts to settle down. Now, how to do this in an easy way? Well, we can use this formula, or we can use this calculator. Okay, so we can take the calculator. Okay, there's no trig involved here, so we don't have to worry about radian mode or anything. Okay, and we can just basically just put this in the calculator. But what I'm going to do first is I'm not going to put it in like this. I'm going to press 2.5 and I'm going to press equals. So that's basically the last answer in our calculator, 2.5, right? So I'm going to set this up in a way that will make it easy so we don't have to keep typing in numbers all the time, and it'll make it accurate as well. So I'll put 3 times 3 brackets 1 minus e to the power of, so this button here, e to the power of, whoops, e to the power, didn't press shift properly, e to the power of negative, I'm going to put answer. Okay, so that basically will put 2.5 in here. We'll put the value of 2.5 in this place over here. When I press equals, it's going to give me what P2 is. Okay, which is 2.75374. So we'll have to give it to 4 decimal places. So 1, 2, 3, 4. So 2.7537. 2.7537. 2.7537. All right. And P3 is found now by putting this value back into here. Now, what it is you don't have to keep showing that you're doing this every time. Show that what you done one time, and then the rest of the times, you can just write down the answer. So you can just press equals now from now on. So now when I press equals, it's going to put this number in that place because this is the last answer. So it's going to keep putting the new answer back in into that position. And that's exactly what we're looking for here to find the values. And what you'll notice is when I press equals again, it becomes 2.8089, 2.8089. Okay, then I'm going to press for P4, I'll press again. So when I press equals again, it's 2.8192, 2.8192. You'll notice that what happens is as you go further and further, it starts to settle down to a fixed kind of, they settle down and fix to certain values. So press equals again, it's 2.8210, 2.8210, 2.8210. I keep going. So I take my calculator and I'll press equals again. 2.8214. 2.8214. Now we can see quite clearly that, up to the second decimal place, that's going to be 2.82. If we carry on, just do another one to make sure. You press equals again. 2.8214. So it's settled down again, right? So we can kind of stop here and we can say, therefore, okay, P is equal to 2.82 to 2 decimal places. They went up to 2 decimal places, so we give an answer to 2 decimal places. Okay, so that's, one way of doing it. All right, now, they normally in the mark scheme talk about showing or justifying that your answer is this to 2 decimal places. It's not normally really asked explicitly as a question in Cambridge. In Edexcel, they do some question might say, justify that your answer is 2.82 correct to 2 decimal places. Justify that the root is 2.82 correct to 2 decimal places. And I'm just going to explain the basis of that so that everyone understands how that works. And we'll just, just to make sure that your understanding is complete. So what you do is you take the upper and lower bound of 2.82. So 2.82, its upper bound will be 2.825. And its lower bound will be 815, sorry, 815. So you have 2.815 and you have 2.825. How did I find those? Basically, I saw that it's been rounded to 2 decimal places. So it's been rounded to 0.01. I divided that by 2. That gave me 0.05, sorry. And I added that to this number to give me the upper bound. And I took away from this number to give me the lower bound. So when I added 0.05 to this number, it gave me 2.825. When I took away 0.05 from this number, it gave me 2.815. So that's the upper and lower bound. So basically what that means is that the root, what we're saying, when we say it's 2.82 corrected 2 decimal places, we're saying that the root lies somewhere between these two values, okay? And then when you round it to 2 decimal places, it becomes 2.82. When you round anything in these between this range, you round it to 2 decimal places, it will end up being 2.82. So wherever it goes between these two values, anywhere that it goes between these two values, for example, it ends up in a number over here, whatever that number is, when you round it to 2 decimal places, it's going to become 2.82. Okay, so how do I show that that works? Well, we go back to our FP. So we say f of 2.815 is equal to, so we go back to the original, this equation that we formed, p minus, so I'll just write FP equals 2 minus, sorry, it's P minus, and then you had 3 times 1 minus e to the power of negative p, right? That was the iterative, or that was the formula that we formed to talk about the roots, right? So now what we're going to do is we're going to put f 2.815 in here, and it should give us a negative value. So we have 2.815 minus 3 times 1 minus e to the power of minus 2.815. Okay, and that should give us a negative value. And we put f of 2.825 in here, which is the upper bound. You have 2.825 minus 3 times 1 minus e to the power of minus 2.825. And that should give us a positive value. They should give us opposite signs, basically, right? So let's see what happens when we use a calculator and put that calculation in. So we're going to put 2.825 minus 3 times 1 minus e to the power of minus 2.825. I'll put 1.5 first. Okay. And then close that bracket. All right. And that gives us a negative value, negative 5.28 times 10 to the power of minus 3. Negative 5.28 times 10 to the power of negative 3. All right. And then we're going to take this and change this to a 2.5 instead of a 1.5. So negative 2.825 and here 2.825. When I press equals, it should be positive. It is. That's good. So 2.93. So positive 2.93 times 10 to the power of negative 3. So we can see that between these two values, okay, there is a change in sign. So between the same kind of statement we wrote above, P equals, or we can say F 2.815 and F of 2.825, there is a change in sign. And FP is continuous. And FP is continuous. Therefore, the root is 2.82 to 2 decimal places. Okay, anything that comes just before 2.825, remember upper bound means anything just less than, that's why I left that open. So anything that is going to be just less than 2.825, so like 2.82 4999, for example, and ranging from that all the way back to 2.815. If you round any number in that range, it will round to 2.82 to 2 decimal places. So as there's a change in sign between those two upper and lower bounds, you will see that there must be a root somewhere between them, which is and the root must be 2.82 to 2 decimal places. Okay, if you round to 2 decimal places, that would be the root. So there's the answer to this question. Okay, I hope that was clear. So you don't really have to do this thing in the end, this justification part in Edexcel, unless they really ask you to it. It is mentioned in the mark schemes, okay, as a way of showing that 2.82 is the root. Okay, but here they're kind of explicitly telling you write to 4 decimal places, everything, so keep writing until you see it settles down to 2 decimal places, add that value. And if you want to make sure, you can do this to make sure. And that concludes this question. Other questions from this paper will be found in the playlist that will appear at the top right of this screen at the end of the video. Other questions from the topic of what we did in the first page, which was dealing with differentiation from P3. Okay, and in particular, I'll put here the product and quotient rules. I'll make a separate kind of playlist for just product and quotient rules for P3 differentiation of Cambridge. And on the top here, I'll put a playlist dealing with iteration. Okay, and so that's basically our setup at the end of the video. Thank you for watching and see you soon.